All right, so let's look at an example here for a typical free fall style problem, one-dimensional. So here we have a heavy rock that is dropped from rest. Okay, so at the top of a cliff and falls 100 meters before hitting the ground. Oops, sorry about that. Okay, how long does the rock take to fall to the ground? What is its velocity when it hits? Man, sorry. Can't really speak very well. All right. So, a couple things here in terms of what we're given and what we're trying to solve for, right? So, it looks like how long does the rock take to fall? It wants us to solve for time. For it to take to fall and its velocity when it hits. Okay, so let's see. First things first, let's draw a diagram. All right, so here we are dealing with one-dimensional motion because the object falls straight down, this rock. So since the object falls straight down, I'm going to call downward positive. All right, well, actually, I'll call that my positive x direction. All right. So our rock starts up here, and then it travels and it falls to the ground, where the other moment we're interested in is right when it hits the ground. Or actually the moment we're interested in is the moment right before it hits the ground. Right? So typically when a problem here says what's the velocity when it hits, it really means what's the velocity the moment before it hits the ground. Right? Because otherwise the problem's going to be pretty trivial because the rock's going to come to rest. So the velocity would be 0. So it's not what it's asking for. It's asking for what's the velocity the moment before it hits the ground. So writing down what we know in this problem, right? So I'm going to call up here my initial, and at the bottom here my final. Oops. So why am I doing that? Why am I choosing those two moments in time for this motion? Right? So first, it tells us a lot of information about where it's dropped from. So that's why it's used to call that my initial. And then since we want to know how long it takes for it to fall to the ground and velocity when it hits, that's going to be that location there at the bottom. But that spot's going to help us solve both of those. So listing what we know. So since we're dealing with kinematics, we're dealing with position, velocity, acceleration, and time. So my initial location, x naught, all right, it's going to be some value, and my final location is going to be some other value. All right, so let's see. We're told that the top of the cliff is 100 meters from the ground. What's going to be useful for me is, since I'm calling downward positive, it's going to be useful to call my initial location 0 and my final location 100 meters. All right, you're welcome to not do that, but just be careful because we're calling downward positive, then that bottom location becomes my 100 meters. Let's see, then my initial velocity, it's dropped from rest. Right here it literally says dropped from rest. A lot of times they'll just say it's dropped. That implies from rest. So initial velocity is 0. Final velocity, we don't know. It's one thing we're trying to solve for. And let's see, acceleration. All right, so the acceleration is constant throughout its motion since it is in free fall. And that acceleration is equal to g. And since downward is positive and the acceleration due to gravity points downward, then I have a positive value for g. All right, so this will end up being our 9.8 meters per second squared. Oops. Keep clicking on different buttons. All right, so let's first solve for time. And looking at what we know and what we don't know. Oh, time is a question mark. All right, sorry, I forgot to write that down. So solving first for time and the fact that we don't know final velocity, let's then use the position equation to solve for this. So that's x equals x naught plus v naught x times t plus 1/2 our acceleration times time squared. Right, so next step is plugging in values that are 0, and also allow you to plug in any symbols here as well. So zeros, we've got initial position is 0, initial velocity is 0. And then these symbols, well, I'm going to plug in for my acceleration g. So we have that our final position is equal to 1/2 gt squared. So rearranging here, solving for t, so I multiply by 2 on both sides, divide by g, and take a square root. So we end up with t being 2x over g square root, right? You can take a couple more steps in the algebra, but I didn't here. So we end up with plugging in numbers, 2 times x, well, that's 100 meters for how we defined our variables, divided by g being, so I actually in my computations used 9.8 meters per second squared. It'd be a lot easier here to use 10, the math becomes a lot simpler, but since I already did this, I'm going to keep writing it. And looking at sig figs, looks like the only number we're given is the 100 meters. I'll assume that's precisely 100 meters. And so that becomes 3 sig figs in seconds. So it takes about 4.5 seconds for this rock to reach the bottom of the cliff. All right, so a couple things here. All right, it's easy in this problem to forget. So we're solving it so that downward is positive. So it's easy to kind of mix up negative signs here. So if you had accidentally thought that we have an acceleration of negative g based on how we define our situation, well then we would have simply one negative sign here in our problem, which would be bad because we have a square root of a negative number. That gives us an imaginary number, which in the physics we're going to be dealing with is unreasonable, especially for time. Time is never going to have an imaginary value. So you always want your negative signs to cancel out so that whatever is in the argument of your radical is going to be a positive value. So, for example, if you had called upward positive, what you might have then is a negative value for the what you're going to plug in up here and a negative value here, so they both cancel. All right, so let's move on here. Let's find the velocity when it hits. All right, well, my gut says to use the velocity equation because it's shorter. So we have our final velocity is equal to our initial velocity plus our acceleration times time. Acceleration, positive g. Initial velocity is 0. So that's just simply simplifies to g times t. All right, so plugging in numbers, 9.8 meters per second squared multiplied by our 4.52 seconds gives us a value of 44.3 meters per second. All right, so we found that this value is 44.3 meters per second, and this is actually what we're, since it asks for velocity, I boxed a little bit too early, right? Because this here, 44.3 meters per second, would represent just speed, where speed is going to be the magnitude of the velocity. We need to also indicate direction. So since at this moment in time in the motion, our object is moving downward just before it hits the ground, the direction is downward.